Hi, my name is Mehradin Alizadeh, and I'm going to present my reproducibility study of the following paper, Deep Learning for Symbolic Mathematics, as the course project of ESCS 6322. Here is the agenda of my presentation. I start with the problem description. Then I move to an explanation of the dataset. The deep learning-based model and the choice of hyperparameters becomes afterward. Finally, I wrap up my presentation with a demonstration of my results and a quick discussion. Symbolic mathematics refers to the task of producing a desired mathematical expression which consists of mathematical symbols, given an input expression of mathematical symbols with respect to a particular problem. In this project, I only consider the mathematical integration problem. Symbolic integration can be considered as a target for NLP models, where we have an input sequence of symbols and want to find a mapping that produces the desired target sequence. The authors propose the following method. We first convert an infix representation to a prefix representation. Since for prefix representation there is no need for parentheses, the length of the sentences will be shorter, which makes the training process faster. The prefix expression then feeds to a sequence-to-sequence model. This model then outputs a prefix expression, which is considered to be the primitive function of the input function. Finally, the prefix representation converts to the infix human-readable representation. The third row shows an actual example from the dataset. These are the main results of the paper. In the first table, they reported the accuracy of their method on 5,000 test datasets. In the second table, they compared the performance of their model with famous computer algebra systems like mathematics. These results are supposed to support the main claim of the authors, which is that deep learning-based symbolic computation has advantages over computer algebra systems. Due to the significance of these results, I was motivated to study their reproducibility. In particular, I tried to reproduce the results of symbolic function integration with greedy decoding on BWT datasets, which reported to be 98.4% accurate. The authors of the paper published their dataset. The process of generating the data for this dataset is as follows. We first sample a random function f. Then we calculate its derivative using SymPy and call it f prime. Next, we add the pair f prime and f to the dataset. This method tends to produce long problems with short solutions. Here are the statistics of the dataset as well as an example line of that. Same as the paper, I used the transformer architecture with the following hyperparameter as the sequence-to-sequence model. I ran the experiments on Google Cloud instances. Here is the summary of my hardware and experimental setups. To clarify, in the first experiment, MK84, I trained the model on the combination of test and validation data. Thus, during evaluation, the model had already seen the test and validation data. This wasn't the case for the rest of the experiments. These experiments can be grouped into two groups. In the first four experiments, I was trying to examine the overfitting and generalization ability and sample complexity of the model. In the last two experiments, the main goal was to reproduce the mentioned results. As you can see in the next slide, I achieved 95.8% consistent accuracy in the last experiment. Here are the figures of training, test, and validation loss, and test and validation accuracy of the experiments. In the last two experiments, I achieved satisfactory results. The final result of this project is the result of the last experiment, in which I achieved the 95.8% consistent accuracy, which is within 2.6% of the reported value of the paper. Since this result is considerably higher than the mathematical performance on the same task and dataset, this result supports the author's main claim, which was that using a deep learning-based model for the task of symbolic integration has advantages over other methods. Thank you for your attention. I hope you enjoyed my presentation.